Hey folks, Steve the Math Buddha here, and today we are going to be having a lot of fun with modular math. Now I think most of you are probably familiar with this rule for divisibility by 3. How do you check if a number is divisible by 3? You just add the digits. If the sum of the digits is divisible by 3, then the number is divisible by 3. Well, what we're going to do today is we're going to use modular math to prove that. We're also going to use modular math to develop a test to see if a number is divisible by 11. Now, there are a few things that I have to show you before we can actually get to that point. There's a lot of buildup. Number one, I got to define this term for you. A congruent to B mod n. Number two, I have to prove that that is in fact an equivalence relation. And finally, and this is where the real fun comes in, I have to prove this last point to you. Congruent numbers are interchangeable. So what do I mean by that? What I'm saying is that in any expression where you have addition and multiplication of integers, you can take any number in that expression and replace it with any congruent number, and you will get a congruent expression. And because congruencies are transitive, you can make as many adjustments as you want. You can substitute any or all numbers with congruent numbers, and you will end up with a congruent expression. Now, you could conceivably just jump ahead to the good part where I show you how to use mods to solve these problems. But you really do need to understand this term, so you definitely have to hang out and check out what that term means if you're not familiar with it. And you might not understand why I'm able to do the things that I'm doing if you don't see this buildup. But I'm going to leave it up to you. What does it mean to say A congruent to B mod n? Well, if A, B, and n are all integers, that's what our capital Z means. That's our symbol for integers. If A, B, and n are all integers with n greater than 1, then we say that A is congruent to B mod n if and only if A minus B is divisible by n. And just to be clear, another way we could say that is that there exists an integer k such that A minus B is equal to kn. Now, anytime we use the 3 bars, it implies an equivalence relation. And the next thing we're going to do is prove that congruencies mod n do in fact meet the definition of an equivalence relation. We're going to have to because we're going to use those properties in our work today. So what are the 3 properties of an equivalence relation? The 3 properties are the reflexive property, the symmetric property, and the transitive property. The reflexive property says that every object is congruent to itself, i.e. we must have A congruent to A mod n. And of course that's true because A minus A is equal to 0, and 0 is divisible by any non-zero integer n. The symmetric property says that our congruency can be switched, i.e. if A is congruent to B mod n, then B must be congruent to A mod n. And that must be true because if A minus B has the form kn, where k is an integer, then B minus A has the form negative kn, where negative k would certainly be an integer. Finally, the transitive property says that if A is congruent to B mod n and B is congruent to C mod n, then A must be congruent to C mod n. Now this one's a little more complicated, so let's write it out. If A is congruent to B mod n and B is congruent to C mod n, then that means that we have integers I and j such that A minus B has the form in and B minus C has the form jn. So let's add those 2 equations together. If we add those 2 equations together, check out that left-hand side. The b and the minus b will cancel out, so we're left with A minus C. Now let's take a look at that right-hand side. On the right hand, we have an in and a jn, so using the distributive law, we jam that I and that j together and multiply it by n. So we have A minus C equals I plus j times n. Now once again, I plus j would have to be an integer if I is an integer and j is an integer, so we do in fact have A congruent to C mod n. So we have our equivalence relation. And now we're at the nuts and bolts of this whole thing. The idea that congruent numbers are interchangeable. That's the concept that we're going to be using to solve our problem. So let's see why it's true. Now the basic idea behind this concept is these 2 rules. You can add the same integer to both sides of a congruency, and you can multiply 2 sides of a congruency by the same integer. The first rule is pretty trivial. Adding an x to 2 sides of a congruency doesn't change the difference between the 2 sides of a congruency. If we subtract b plus x from a plus x, we're going to get a minus b, which would be divisible by n if a is congruent to b mod n. Now the second rule isn't quite as trivial, but it's pretty straightforward. If a minus b has the form kn, ax minus bx has the form xkn. If x is an integer and k is an integer, then xk is an integer, so ax would be congruent to bx mod n. Now, the idea that congruent numbers are interchangeable in any expression is just a repetition of this basic idea. Consider, for example, this expression, a times b times the sum of c plus d. If we replace the c with a congruent number c prime, well, by rule number 1, if these two things are congruent, then these two things are congruent. And by rule number 2, if these two things are congruent, then these two things are congruent. So the expression stays congruent. Now, if we want to replace the b with a congruent number b prime, well, again, if these two things are congruent, then by rule number 2, these two things have to be congruent. And by the transitive law, all three of these things have to be congruent. So we could place any and all numbers in this expression with congruent numbers, and we're going to get a congruent expression. We just make the changes as we go along. Every change we make holds the congruency. Before we get to the good stuff, I wanted to take this time to remind you to please like, share, and subscribe and turn on those notifications. I also want to share with you my most recent Zazzle purchase. I told you in my first video that you could literally go onto Zazzle, upload a picture of your cat, and place it on the mug of your choice, and a few weeks later you would get that mug with the picture of your cat on it. Well, guess what? I did just that. Check this out. I have two cats. I got a mug for each cat. This is my Simba. This is my Sally. Let's check out a high-res picture of this. I love these mugs, and Zazzle is quickly becoming my favorite store. There is so much I could do on that site. And I have a link to their Design Your Own Mug page in the description below. Of course, you can't buy these mugs. And why would you want pictures of my cats on your mug? But you could upload any design you want, any picture you want. You could hook up with my Fiverr artist, the dude that created this t-shirt. He'll make a great design for you. And those are the two pieces you need. You have a great designer and a great print-on-demand service, and you could do anything you want. Not just mugs, you could do t-shirts, you could do pillowcases, you could do clocks. There is so much that you could do on the Zazzle website. But whatever you do, please use my links because it helps to support this channel. So now it's time to take a look at the problem that we all came to see. A number is divisible by 3 if and only if the sum of its digits is divisible by 3. How do we use modular math to prove that? Well, the first thing we have to do is we have to rewrite this statement. Another way of saying that a number is divisible by 3 is saying that the number is congruent to 0 mod 3. If a number x is divisible by 0 mod 3, then by definition, x minus 0 is divisible by 3, which is the same as saying that x is divisible by 3. So let's rewrite this statement accordingly. A number is congruent by 0 mod 3 if and only if the sum of its digits is congruent to 0 mod 3. And the way we're going to prove this is by showing that every number is congruent to the sum of its digits. So they're both congruent to 0, or neither is congruent to 0. And let's try this with a concrete example. Let's consider this number, 475,625, which can be written in this way. It's your standard base 10 expansion. And here's the key. 10 is congruent to 1 mod 3. 10 minus 1 is 9, which is divisible by 3. That means, based on the work we did in the last chapter, we can replace all the 10s in this expression with 1s, and we would be congruent mod 3, which means that this is congruent to this. And of course, 1 to any power is 1, so all our 1s just drop out of the expression, and we're left with 475,625 is in fact congruent to the sum of its digits mod 3. Now let's get rid of all this and consider the same example for divisibility by 11. 11 is an interesting case because 10 is congruent to negative 1 mod 11, which means that we can replace each of these 10s with a negative 1 and it will stay congruent mod 11, which means that this is congruent to this. Now, negative 1 to an odd power is always negative 1, and negative 1 to an even power is always 1. So we end up with this alternating sum where we alternate between positive and negative numbers, which means that this is congruent to this. And what I like to do is gang the positive terms and the negative terms together, which means that 475,625 is congruent to 18 minus 11, or 7. 475,625 is congruent to 7 mod 11. So 475,625 is not divisible by 11. It's congruent to 7 mod 11. So before we go, I want to take a look at this one last problem. We're running a little long, but I think we can squeeze this in. And I really want to look at this problem because it's a lot of fun and it introduces a really important concept. What is the remainder that we get when we divide 10 factorial by 11? Now keep in mind that remainders are all about congruencies. When we divide 10 factorial by 11, we get a quotient q and a remainder r that satisfies these parameters. So when we subtract r from 10 factorial, we get a multiple of 11, 11q, which means that 10 factorial is congruent to r mod 11. That's what we're looking for. We're looking for the number from 0 to 10 that's congruent to 10 factorial mod 11. And the way we're going to do it is we're going to rearrange our product like this. And why am I grouping these particular numbers together? Well, 2 times 6 is 12. It's 11 plus 1. It's congruent to 1 mod 11. Same thing with 3 times 4. It's 12. It's congruent to 1 mod 11. 5 times 9 is 45. It's 44 plus 1. It's congruent to 1 mod 11. 7 times 8 is 56. It's 55 plus 1. It's congruent to 1 mod 11. So every one of these products can be replaced with a 1. It's going to stay congruent mod 11. So we get 10 factorial congruent to 1 times 1 times 1 times 1 times 10 mod 11. Or 10 mod 11. 10 is the number we're looking for. That's the remainder we get when we divide 10 factorial by 11. Now the concept that we're illustrating here is inverses. 2 and 6 are inverses mod 11. If all we care about is what 10 factorial is congruent to, then the 2 and the 6 cancel each other out. They drop out of the product. And because 11 is prime, what we're going to have is that every integer x from 1 to 10 is going to have a unique multiplicative inverse y from 1 to 10 that satisfies x times y congruent to 1 mod 11. Even 10 has an inverse. We couldn't pair 10 off with its inverse here because 10 pairs with itself. 10 is its own inverse. 10 is congruent to negative 1 mod 11. So 10 times 10 is congruent to negative 1 times negative 1 or 1 mod 11. It's a really interesting concept that I really want to use in future videos. But for now, I think it's really time to get to our closing. So I really hope you all enjoyed my modular math video. As usual, please let me know in the comments what you thought. And in particular, do you think it's taking me too long to get to my promised subject matter? That's something that's concerning me. But I really did want that build-up. I think it's important. I wonder if even maybe I'm going through the build-up too quickly. I give you the channel markers and an option to jump ahead, so maybe the people that stick around want to see a slower, more detailed build-up. There's also the call to action segment, which could be a little lengthy at times, and I'm sorry about that, but I have to support this channel. This channel does not run without your support. Please let me know in the comments what you think. I rely on your comments for this channel. I really, truly do. And that's all I have for you today. This is the Math Buddha signing off. Have a great night and have a truly pleasant tomorrow.